Right now, the sound of my voice is traveling to your ears, and the light from whatever screen you're watching this on is traveling to your eyes. And both of those things are happening because of waves. It's one of the most fundamental ways energy moves through the universe. So how does it all work? Well, let's break it down.
Okay, let's start with a bit of a riddle. What on earth could possibly connect the sound you hear from a guitar with a beam of sunlight? I mean, on the surface, they seem like they couldn't be more different, right? But stick with me, because by the end of this, you're going to understand the surprising and honestly really cool link between them.
So the answer is pretty simple. They're both waves. But, that just leads to a much bigger question, doesn't it? What exactly is a wave?
Okay, so here's the absolute key. A wave is a disturbance, but it's a very special kind of disturbance. Its whole job is to move energy from point A to point B without actually moving any physical stuff, any matter along with it. So you can think of it like a delivery service for energy, not for packages.
You've seen this a million times, I'm sure. Picture a stone hitting a perfectly calm pond, and those ripples spreading out in perfect circles. Now imagine a little leaf is floating on the water. What does it do? It just bobs up and down, right? The leaf doesn't travel with the ripple. And that's the perfect illustration. The energy is moving across the water, but the water itself just kind of stays put.
So now that we've got a handle on what a wave is, we can go a level deeper. It turns out that pretty much every wave you can think of falls into one of two big families. And what separates them is just one single, simple difference.
On one side, you've got mechanical waves. These guys are a little needy. They absolutely have to have a medium, some kind of substance, like air or water or the ground, to travel through. And on the other side, we have electromagnetic waves. These are the cosmic travelers. They don't need anything to travel through. They can just cruise right across the total vacuum of empty space.
All right, let's zoom in on that first family for a bit, the mechanical waves. Because even inside this group, they've got two very different and pretty clever ways of getting around. First up, we have transverse waves. The key word here is perpendicular. All that means is at a right angle. So in a transverse wave, the little particles of the medium are moving up and down, while the wave of energy itself is moving forward. The perfect way to picture this is making a wave on a rope. You've probably done this. You hold one end, you flick your wrist, and you send that hump of energy traveling horizontally down the rope. But if you watch any single little piece of the rope, it's just moving vertically, up and then down. That's a transverse wave in action.
Now, the second type of mechanical wave is called a longitudinal wave, and its motion is basically the exact opposite. Here, the particles vibrate parallel to the direction the energy is going. So instead of that up and down motion, they get pushed and pulled back and forth.
And the classic example of this is sound. When I talk, my vocal cords are creating these vibrations that push and pull on the air molecules. This kicks off a chain reaction of compressions, these areas where the molecules get all bunched up, and that chain reaction travels right into your ear. The energy moves forward, and the air particles just shuttle back and forth in that very same direction.
So let's do a quick recap. For a transverse wave, think perpendicular. Particles move up and down, creating those classic high points and low points we call crests and troughs. For a longitudinal wave, think parallel. Particles move back and forth, creating those bunchy areas of compression.
Okay, now for the fun part. Let's get the toolkit, the actual language we use to describe and measure any wave. This is the basic lingo of wave physics, and once you get these few terms, you can pretty much describe any wave in the entire universe.
First up is wavelength. It's super simple. It's just the physical length of one full wave cycle, so the distance from one peak to the very next peak.
Next, we've got frequency. This just tells you how often the waves are coming. If you stood in one spot and counted how many waves passed by you in 1 second, that's its frequency. We measure it in something called hertz.
And finally, there's amplitude. This is all about the wave's power, or its intensity. For a sound wave, a bigger amplitude means a louder sound. For an ocean wave, a bigger amplitude means a taller, more powerful wave. Simple as that.
And here is where it all comes together just beautifully. This simple little equation shows us that a wave's speed is just its frequency times its wavelength. These three things are totally connected. If you change one, another one has to change to keep everything in balance. It's so elegant!
Okay, we've got our toolkit. We know the language. Now let's zoom back out and talk about that other family of waves, those cosmic travelers, the ones that don't need any medium at all. This is where things get really, really cool. Welcome to the electromagnetic spectrum. It's like a vast, invisible rainbow of pure energy.
It includes everything from the radio waves carrying our music and data, to the microwaves that cook our food, to the visible light that lets us see the world, all the way up to powerful X-rays and gamma rays that let us see inside our own bodies or study distant galaxies. Isn't that incredible? They all seem so different, but they're all the exact same fundamental thing: pure energy traveling as a wave.
And that brings us all the way back to where we started. So what connects a guitar chord to a sunbeam? Well, now you know. They are both waves, and they both have one job: to move energy. The guitar string creates a mechanical wave, sound, that moves energy through the matter of the air. The sunbeam is an electromagnetic wave, light, that moves energy right through the empty vacuum of space.
So we've seen that waves are just everywhere. They're the universe's energy delivery system. It's just this powerful idea that connects so much of our world. And it leaves us with one last, really fascinating question to chew on. If waves are just energy in motion, what happens when that motion stops?